Okay, great. Okay, so I'll be introducing our speaker for the day. So we have Dr. Pieter Neethling. He did his studies at Stellenbosch University, so he did his undergrad and postgrad here, and completed his PhD in 2008. Following this, he did a postdoc at Stellenbosch University, and a year after that, he was doing lecturing part-time, and in, I think it was 2012, Dr. Neethling was appointed as a lecturer at the department, and he got bumped up to a senior lecturer in 2017. And during his time, he has supervised and co-supervised 15 master's students and 11 PhD students. He also has published 36 peer-reviewed journal and conference papers. And currently, Dr. Neethling is the director of the Laser Research Institute, and he is the chairman of the Photonics Division of the South African Institute of Physics. So we really are truly honored to have Dr. Neethling here, who is an expert in spectroscopy, to tell us all about it. And yeah, please give us a warm welcome to Dr. Neethling.
Thank you, Sam and Kelsey, and thanks for organizing this. I think it's a really great event, and if you look at the turnout as well, it's clear that there's some interest in this. It seems a bit low. There we go. Okay, so first of all, welcome. Yes, International Day of Light. So, what I'm going to try and tell you today is just, lights. I'm going to try and tell you today a little bit of overview about some ideas behind spectroscopy and what spectroscopy is. I see it's quite a diverse crowd, everything from first years to professors, so feel free to stop me and ask questions along the way as well, so I really don't mind. Okay, so but maybe let's start off International Day of Light. What is it and why do we do it? Okay? So it's a UNESCO sanctioned, so the United Nations Educational and Science and Cultural Organization sanctioned day. And basically, it celebrates the achievements of light. Okay? How light has influenced society in all aspects, in a certain sense. How it brings people together, how it advances technology, and so forth. If you go on their website, a lot of you might not know, but if you study history of science a little bit, there was this guy. I'm not even going to try and pronounce his name. He did all his work in Africa. He was based in Cairo, born in what is today Iraq, but based in Cairo. And he published a book in 1015 called The Book of Optics, literally what it is. And people like Newton and Kepler and everybody, all the famous names, they used his book. Okay. All right. So Africa has a rich tradition of optics and science, and we sometimes tend to forget that. Okay. Why are we celebrating this on the 16th of May? Well, the 16th of May is the commemoration of the first successful operation of the laser in 1960 by Theodore Neyman. Okay, so that's the reason for the day. But I think it's just a nice opportunity to say, well, listen, here is science. Science is wonderful. Science is really bringing people together, and it's really advancing technology, and that's why we do it. Okay, so let's get back to my talk. Okay, so I'm going to talk a little bit about spectroscopy in general. So what I've got here on the screen are two pictures of the sun. Okay, light. We need light to do spectroscopy. And what I like about these two pictures are, if you just look at the one on the left, if you stare directly at the sun, don't do this at home, it's obviously very bright. You can even see the camera slightly super exposed. Okay? As you move your eyes away, the shade, what you observe changes. So it goes from a very light blue to a very dark blue if you move in that direction. If you move in this direction, eventually you reach a cloud, which is nice and white. Turn this down a little bit more. Okay, nice and white. Here the cloud is kind of grey, but immediately you see that the picture looks different depending on where you're looking. In other words, what did the light encounter? If you look at this picture on the right, it's the same sun. Okay? Picture looks completely different. And we can immediately actually, I've always found it interesting, that you can immediately look at a picture like this and you know it's sunset, not sunrise. Okay? Why? Why do we know it's sunset? Because we are familiar with the colors, the shades that we observe here. But it's the same sun, but it looks completely different. So clearly we see that as the light interacts and moves through different media, different matter, it changes. Okay, what reaches your eye changes. Okay? And this is the essence of spectroscopy. We use light, we let it interact with matter, and we look at how the light has changed. Simple as that. Okay, done. We can go home. Right? That's spectroscopy. Okay? What I want to do today is I'm going to show you a couple of examples from our laboratories, so what we do here at Stellenbosch University, and just a little bit more in general about how spectroscopy might influence your everyday life, how you interact with it sometimes, I guess, without even knowing. Okay, so fascination. We've always been fascinated with light. So this is the Sainte-Chapelle Cathedral in Paris, where the king stayed, I believe. And this is in the Pink Mosque in Iran. And what you'll notice is that people have been exploiting this interaction of light and matter for a variety of purposes. In this case, art and culture and faith and religion, right? I mean, it's pretty, but all that it really is in the end is that you're saying, well, I've got this big light source on the outside, the sun, and I'm filtering it in a specific way, which I want to, in order to create beautiful patterns on the floor or against the wall or whatever the case might be. Okay, so we've been manipulating light for centuries. Okay? And as I said, this essentially is what spectroscopy is all about. Okay, so the sun is all good and well. The sun is still a very useful tool for doing spectroscopy. But we're fortunate that in the laboratory these days we've got access to a whole host of light sources. Okay, so at the top here, what I've indicated, or I have a picture of here, is a couple of LEDs. Light-emitting diodes, and these days you get them in all different colors. So you can basically pick your color and you can go buy it off the shelf. And the same goes for lasers. They're based very much on a similar technology. It's actually quite fascinating. When I saw this picture, I thought back to when I started my master's degree here, and that's about 20 years ago. These things weren't available, right? You had very, very specific wavelength lasers available commercially, and they were freaking expensive, right? You basically were limited to what you could do based on the lasers available. These days, you can go on Amazon, you can buy any of these ones. Done, right? Pretty easy, and they're cheap as well. But technology has advanced massively, so this is a little video taken from our laboratory where we can now generate laser light of essentially any wavelength we want. Okay? We can send it through specialty optical fibers, that's what we do here. And if you know what you're doing, you can generate a light pulse on the outside which contains any or all the wavelengths that you could possibly be interested in. And of course, these now become extremely useful tools to do material studies, to do spectroscopy, and to do our science. Maybe just as a little side note, that little LED over there, yeah, that's Nova Horizon 2014. So any white LED, any LED in your home, any light emitting diode, you know, all of these, you replace all your light bulbs with these LEDs. That's based on this one. Okay, gallium nitride LED, which emits in the blue, which is what you require to make the white light LEDs that you've got there. Okay. So I'm a physicist, so when you approach a problem like spectroscopy as a physicist, you kind of try and break everything down into its smallest little parts so that you can piece it all together and think about how you want to approach it. So when I think about the properties of light, I like to think about it in terms of a parameter space. How can I pick the properties in order to achieve what I want to do? So if I think about light, I can think about the wavelength of the light, or the color if you want. I can think about the bandwidth. Is it a single color, or are there many colors? Right? So this little green laser pointer is a very narrow bandwidth. It only emits at 550 nanometers. But I can also generate a white light source like these lights over here, which generate a very broad bandwidth, many colors. I can think about the polarization. So polarization has to do with the orientation of the wave. So light is an electromagnetic wave, and the wave can oscillate in different planes. And depending on the plane that it's oscillating on, I can ascribe a polarization to it. I can think about the intensity. How much light do I have? Only a little bit. Single photon spectroscopy is a thing these days, where you use single photons to do your work, or you can use enough intensity to start ablating material, destroying it, vaporizing it in certain sense. I can go continuous or pulse. So this is a continuous wave laser. The light is on continuously when I switch it on, or I can generate it in very small short pulses. So in the labs downstairs, we can generate pulses which are 1 or 110 to the power of minus 15 seconds in length. So very, very short pulses. And of course, your interactions can change. What's been interesting of late that people have also started playing around with the spatial profile of light. So if you look at this little laser pointer, it's pretty round. That's not all that interesting. But I can change that and shape that, and by doing so, I can again play around with how the light will interact with the sample that's going to shine on from an angle. And I can do that both in space and in time. So in the labs downstairs, we're playing around quite a bit with the temporal profile of the laser pulse, how it looks in time as it propagates, and thereby trying to control certain chemical processes. Okay. So on this side is my parameter space of light. This is all the things I can change, I can play around with, I can manipulate if I want to do an experiment. On the right are, I don't think this is all of them, but these are the ones I could think of last night. The types of interactions when light interacts with me. Okay? So the first three are pretty straightforward. It can be absorbed. Okay? You go through a material, and that what isn't absorbed is transmitted, and that what isn't absorbed or transmitted must be reflected. So those three things kind of go together, but you could use each one of those three as a signal to investigate material. Then there's some other things that can happen. Light can be refracted, okay? So that is, light is bent, and that's the measure of the refractive index of the material. It can be scattered. So depending on the size of the object that you're going through, light can be scattered. So the clouds that we saw earlier is a good example of that. And this scattering can either be elastic or inelastic. So what do I mean with this? Well, elastic means no energy is lost to the system. So if you come in with green light is scattered. And if it's inelastic, it means it converts a little bit of that energy to the sample. And if a little bit of the energy is to the sample, it means the wavelength of the light changes. So this is a really interesting field of study. It's called Raman spectroscopy. It's another project that I am involved with. Okay. Then you can get things like fluorescence and phosphorescence. So fluorescence, I've got a little demo here. So if I shine a UV torch on this little sample, you can see it emits light at a different wavelength. If I take the same and I shine it on a different sample, it emits in a different way. Okay, so this is fluorescence. This is absorbing the light, but emitting it again in a different wavelength region. And again, I can get information from the sample based on how that light looks. Phosphorescence is very similar to fluorescence, it's just on a different time scale. And then lastly, what we've got access to in the labs is nonlinear interactions. It's when matter stops behaving in a linear fashion, and the interaction becomes dependent on what the intensity of the light is. Okay? And that's a really interesting field, and we've got access to that with high intensity lasers. So you see that if I had to give a talk covering this, we'd be here next week. Okay? There's no chance. So what I tried to do is just highlight a couple of these ideas and give you a bit of a flavor about what is possible. So what I've done is I've picked a number of applications where I've looked at different regions of the electromagnetic spectrum, so different wavelengths. And then I'm grouping absorption and transmission and reflection together because they kind of are different flavors of the same thing, as well as fluorescence spectroscopy. Okay, so we better get going, otherwise we will. So in my title, I promised you to talk about galaxies, right? So there's some galaxies. Okay. Basically, everything we know about outer space is because of spectroscopy, right? We have, up till very recently, when gravitational waves was discovered, there was no other way, oh, and of course a couple of rocks that fall on the Earth every now and then, but except for that. There's no other real way of getting information from outer space. We've got these really bright objects, stars, that emit a lot of light. All we have to do is say, well, the light passes through stuff. In this case, these are cosmic clouds, so interstellar clouds. And as it passes through these clouds, the light changes. And we can measure these changes. And by measuring these changes, we can get some information about these clouds. Okay? And that's a very useful tool. We study extraplanetary atmospheres in this fashion. Right? There's lots and lots of application to this. Okay, what Dr. Steenkamp did for her PhD, so those of you that are in the physics department probably know Dr. Steenkamp. So she started this project during her PhD, and she supervised a couple of students to completion on this as well. She looked at carbon monoxide, and you can ask yourself, why carbon monoxide? Well, it turns out carbon monoxide is the second most abundant molecule in the universe. Hydrogen, of course, being the most abundant, H2, and CO being the second most. Okay? So if you're looking at an interstellar cloud, dust cloud, it contains a lot of carbon monoxide. It's bound to. So the idea there simply is saying, well, let's use this carbon monoxide as a tracer map to look at these interstellar clouds. And there's a lot of information you can get from it. You can get everything from looking at the mass ratio between carbon and oxygen, electron and proton, and there's all kinds of crazy astrophysics that they can do using this information. What is required, though, is you need to know exactly where does carbon monoxide absorb in the lab, right? Not when it's in outer space moving at some other ridiculous speed. Okay, here. How does it look? And that's really what she did. And if you can do those really accurate laboratory wavelengths, you can compare that to measured spectra. And if you compare it to measured spectra, then you can calculate things like how quick, how fast is the gas cloud moving away from you or towards you, or whatever the case might be, expanding, and so forth. So this is the first little demo I want to do, or second one, I guess, we take the fluorescence. That's why I gave you those glasses. So the sun or the stars are emitting a continuous spectrum. As it passes through the gas cloud, some of that light is absorbed, and the light that is absorbed is a characteristic of that molecules that they pass through. Okay, so you can imagine if carbon monoxide absorbs those lines, they will be missing from the spectrum when it arrives on Earth. We've got a complementary technique called emission spectrum, which is exactly the same wavelength, it's just light being emitted. And you do that with a machine like this one, where if you, I'm going to switch that off so you can look here. If I put this in the electrical discharge, the little gas tube lights up. So that is hydrogen gas, yes, hydrogen gas. So I'm going to switch this off as well. Okay, so it's very dark. Now if you look through your glasses to that hydrogen gas, you should see the line in the middle, and on the sides and the top, because those are funky glasses, you should see very distinct colors, spectral lines, that look something like what you saw on the screen just now. So that's hydrogen. If I move this to neon, so this is going to be neon. If you look at this now, you should hopefully see, oh sorry, this is helium, not neon, helium first. You should see that the spectrum has changed. Okay, it looks different. Okay, more lines and separated in a different way. And if I move this now to neon, so this is neon, looks different again. Okay. So that should give you an indication, right, that this, by looking at the light that passed through this gas now, I can, in principle, calculate such an emission spectrum. Okay, I measure this now, so I know I can identify what gas was there. Now, one of the things why this is useful is that if the gas is moving, and it's moving away from us, all these wavelengths would shift to the red, okay? So-called redshifted. If it's moving towards us, it's blue shifted. So if I measure one of these spectrum and I compare it to the one I measured in the lab, I can calculate how fast it was moving. Pretty cool. Right, so that's to a certain degree what Dr. Steenkamp did. So this is your carbon monoxide molecule, and it's a diatomic molecule, so it can vibrate and go rotate, and all of these crazy things can happen. And she basically looked at what wavelengths does this molecule absorb. And the wavelengths that she uses is here in the far ultraviolet, so 140 nanometers, around about here. Okay, so very, very deep in the ultraviolet. We talk about the vacuum ultraviolet. Air absorbs this, so you have to work in the vacuum. Okay, so this is just the vibrational spectrum that she measured out. If we look carefully and we just examine one of those vibrational peaks, that one over there, you get the rotational spectrum there. So there's energy associated with the rotation of the molecule as well. There's somebody admitting. All right, there we go. Okay, what's interesting here though, I can zoom in a little bit more, and these vibrational or energy levels, so these are the same lines you saw, just obviously a lot more of them and a lot more close to space, belong not just to normal carbon-12, oxygen-16, but to different isotopes as well. Okay? Carbon-13, oxygen-16, carbon-12, oxygen-18, 12, 17. If I zoom in even a little bit more, I can now start assigning these lines to specific isotopes. Carbon-12, oxygen-17, where these ones are carbon-12, oxygen-16. So this is pretty sensitive stuff. And it's really important because it turns out there's so much carbon monoxide in the interstellar galaxies that the carbon-12, oxygen-16, of which of course is the most abundant, would absorb all the light there in its region. So then it becomes difficult to pinpoint exactly what the wavelengths are. So you want these isotopes, which are not very common, carbon-12, oxygen-17, 0.04% abundance, so very, very little. You want them, and you want to measure their wavelengths very, very accurately in order to be able to then compare it to interstellar. And this was the first time that this was done. A couple of papers that she got from this as well. Like interesting, her surname was still Steinman, I think it's before she got married. Okay. So. She now uses these exact same techniques, which she developed for carbon monoxide for an astrophysical application. She does now to do isotope separation, so separating medically relevant isotopes using lasers. Okay? It's a really interesting project that we've started up now, and it's been, see Fricky over there, he's part of that as well. Okay, but it's exactly the same type of spectroscopy, exactly the same principles. And that's to manufacture medically relevant isotopes. Right, next thing. When you think about Stellenbosch, odds are you think about the campus, right? Okay? Maybe you're sitting here. If you are a tourist to Stellenbosch, I promise you what you're thinking about is this and this, right? That's why you're here. Yeah, wine. Okay. So Stellenbosch is obviously very well known for its wine country. It's makes excellent wines. So it's just natural that if you've got a university in Stellenbosch, you should also be looking a little bit at wine. And we do. Okay, so this is work done by Dr. Pieter Neethling. He did it with colleagues at Viticulture and Enology. So the idea there basically is saying, well, when wine is fermenting, the winemaker's got to go, he knows he's got really good grapes, he tested them, that's fine, he's got good yeast, that's fine, he chucks everything into a barrel, closes it up, and prays. Okay? Every now and then he'll take out a little sample and send it for chemical analysis to check that everything's okay, but that's an expensive and time-consuming process. So the whole idea is, can I monitor this fermentation process over time? And then if I see things are going south, can I intervene? And that's basically what they did. So they took wine, and they realized that if I shine light of the correct wavelength on there, that one, right of the correct wavelength on it, the wine will fluoresce. Okay? So you can clearly see I'm shining blue light on there, and that looks pretty greenish, blue-greenish, right? The wine fluoresces. And it turns out this signature, the light that comes from there, you can use to quantify or qualify what's happening inside the wine. So it's a bit of a process, and it involves a little bit of machine learning because wine is a very complicated thing. It contains a lot of phenolic compounds and a lot of stuff which gives it its great flavor and its taste and all of that. So it's very difficult to analyze completely. So you have to take a bit more of a brute force approach. So what do? They basically recorded what is the wavelength of the fluorescence, so that's what you saw, but as a function of excitation wavelength. So I change the wavelength of the light that's incident, and I record the wavelength that is being emitted for each incident wavelength. Then you get a two-dimensional spectrogram like this. Okay, so here we're working not so deep in the UV anymore. We're exciting here from about 250 into the visible, and we're detecting here from the mid-UV into the visible as well. So you see we're moving along the electromagnetic spectrum as we're looking at these examples. Okay, so what is known is that some of these signatures are all on top of each other. We can assign to different classes of molecules. Okay, that's not so important. It's these molecules which gives Wine's flavor. Okay, so you want them in the right ratio and combination and things like that. But even so, you can see it's really complicated stuff. It's overlapping. You can't make heads or tails about it really. I mean, the winemaker will taste it and will say, sharp, it's good, moving on. But of course, you want to do this in situ. You don't want to take out sample salts. I mean, you want to monitor it constantly. That would be ideal. So what they did is they took many, many measurements like this of many, many, many wine samples during the fermentation process. And they feed that all into a machine learning algorithm, and what the machine learning algorithm really does is it looks for patterns in a certain sense. Okay, there's different ways of doing this, mainly principal component analysis in this case, again, not so important. It's looking for patterns. And what they were able to show, and I find this quite interesting, is they took a lot of different cultivars. So if you're into your wine, you'll recognize all of these cultivars. If you're not, they're different types of grapes. That's all you need to know. And you make wine from them. And simply by looking at the must, so that's the stuff in the fermentation chamber, and measuring the fluorescence there, they should separate out all of these different cultivars. And I promise you, if you were to look at this must with your naked eye, they'd all look the same. It's red grape juice. Okay? Good stuff, but it's red grape juice. But looking at the fluorescence signal, you could clearly separate out all the cultivars. Now, this is simple in a certain sense. I mean, cultivars differ by much. But of course, if you now had a fermentation tank and you suddenly saw that your Shiraz is starting to fluoresce like a pinotage, you know things are going wrong. You know you need to step there. Okay, so that's a really nice little application, and I don't know if that doesn't deserve a cheers, I don't know what does. I think that's really important work. Okay, so that's work by Dr. Bosman. So I'll tell you a little bit about one of the things that I've been involved with. So this is work done by a PhD student of mine, Catherine Fukwa, who graduated recently. And it was on peptide structure. Now, peptides are small biomolecules, okay? Small proteins, if you like. And what's interesting about these peptides are the fact that they are considered our next front line in basically treating bacteria and antibiotic resistance. So you all know that our antibiotics of today, the bugs are becoming resistant to them. It's a big problem. Because peptides are natural, okay, your body doesn't seem to develop a resistance to them. So the one we looked at is called penicillin S. Again, not so important. The reason we look at it is because it's a simple one, right? You start simple. It's also a really, really effective one. It's so effective, it's probably pretty useless because if you were to ingest this, you die, okay? It kills everything. Okay? It is used in topical treatments, so if you've got a skin lesion or something that becomes infected, then you can use it for a topical lesion, but you wouldn't ingest it. This is potent stuff. It's a pretty small one. So in terms of peptides and proteins, it only contains 10 amino acids, and it's 5 of them that are just repeated on the other side as well. What's interesting, you might note, is all these NH groups, these amide groups, okay? And it's because they all have this hydrogen on there, and these hydrogens can form what we term hydrogen bonds. So, of course, the molecule doesn't really look like this. It looks a little bit more like this. So those hydrogen bonds are now indicated by these little yellow dotted strippies. Okay, and the idea is that they stabilize the molecule. They make it quite stiff, quite rigid. The molecule itself, if you look at it from another side, has actually got a hydrophobic side and a hydrophilic side, meaning don't like water or likes water. And this is the reason why it acts as an antibacterial, okay? Because a bacteria's membrane is basically a lipid bilayer, which means it's static. And if the hydrophobic side comes into contact with that, it can penetrate, it can disrupt the membrane, and the bacteria dies. Pretty much. That's my biochemistry 101. Okay, so that's what's happening. Turns out the molecule is a little bit small to do that. The layer is a bit thick, so it can penetrate, but can't really go through. So what the molecule does, it stacks, it staggers, it becomes aggregates. So 2, 3, 4, 5, 6, many, okay, big. And then it can do its job. So what we wanted to do is examine this stacking, how these hydrogen bonds form and how they break, actually how they break, as well as the stacking. And the way we did it is with infrared spectroscopy. So here the infrared spectrum is given in wave numbers. That's just another way of denoting frequency. If you were to convert that to wavelengths, we're talking now about 5,800 nanometers, about 6,200 nanometers. So on my wavelength scale, I'm way down here. So we've come from 140 nanometers over there, and now we're way over here. Okay, so we're moving down up in wavelength. So those amides, those NHs, they absorb in this region. And what we examined was if we looked at this infrared spectrum, so this is just an absorption spectrum, as a function of temperature, what do we see? Because of course if you heat something up, you destroy it. That's kind of what we were doing here. So we're heating it up, and we know we're going to break stuff. We just want to see what is it that we break. We're adding energy. And we saw a couple of things. First of all, we saw the peak was moving a little bit to the right, and you saw also on this flank see little changes in the shape of the absorption spectrum. It's subtle, right? Okay? PhD students took quite a while to analyze this. Not easy stuff. One of the easiest ways of analyzing is just taking different spectra. So you take your 20-degree spectra and you subtract all the others from that, and this is what you obtain. Okay, so 20, 30 minus 20, 40 minus 20, and so forth. And now suddenly these changes become a lot clearer. Okay? The shift in peak, not so much, but you can clearly see here on the sides how the spectrum changes. Now you've got to try and figure out what's going on there. And that's where the figure on the left comes in. So what we've got here is a model of the molecule. So there's my molecule again. And what we've done is just we added two more, one at the top and one at the bottom. We simplified the one at the top and the one at the bottom a little bit, because otherwise it gets too complicated. And then we do some quantum mechanical, molecular mechanics calculations on this. Right? You give it to a big, strong computer and you say, go. Right? Literally. You wait a couple of days and it spits out some answers. And the answers it spits out is, what is the energy associated with each of these bonds? So you can go and you can click on any one of these bonds, and you can see what is the energy associated with it. Then you go to your spectrum and you say, I'm looking for an energy associated with this wavelength. I go back to my molecule and I say, which bond was that? And you go look for it. Hop, hop. Gives you a bit of help there. But you've got to kind of have to click through all of them and figure out. And if you see a decrease in absorption, it means there's less of something absorbing light, which means you've taken something away, which means you've broken some bonds. And then you can go see which bond was that, what energy corresponds to that. And that's effectively what she did. So you could see that you were breaking some of those hydrogen bonds, some of those stabilizing bonds that I discussed earlier. If you just look at the peak position, we could see that those peak positions moves as a function of temperature. And you get like this sigmoidal plot. And if you analyze this, you can basically identify two transition temperatures. One here at 43 degrees, and another one there at 57. So it's just this part of it is just replotted on this side. And there's basically the inflection points there, 43 and 57. And by analyzing how the spectrum changes before and below and above and below these temperatures, we can then start ascribing structure, information to how you change the structure. And the first temperature point, that's basically when these stacks of peptides, which we know exist, when they start breaking up. Okay? Completely. So then you basically disrupt it. So past that temperature, there will probably not be very good antibiotics anymore. The second one is when the way that they stack is they stack according to these big phenol rings that stack in so-called beta sheets, and you start disrupting them. Okay, you break the hydrogen bonds there. So the so-called interpeptide hydrogen bonds start breaking there. You can actually measure them. You can do that because you've got this very good model that describes it. Okay. So published this earlier this year, and this is part of an ongoing study. So we're going to start looking at some more peptides, and we've also done some other spectroscopic Raman and on this, which will be published hopefully this year as well. Okay. So yeah. Okay. Next thing I want to just briefly, so this is not work from our laboratory, although we do work in the terahertz range as well. I just thought I'll walk down the spectrum some more. So now we're going further into the infrared, so just before microwaves. Okay? It's called so-called terahertz region. And the reason I want to show this is if you've traveled to the US or Europe in the last, I don't know, 5, 6, 7 years, you would have been experienced to terahertz radiation because you go through those full body scanners and that's what they use. I'll show that on the next slide. But this is a very useful wavelength range, right? We don't really think about it. One application at the moment which people are pursuing severely is communication. Okay? As you, at the moment, your Wi-Fi and everything works here in the microwave region. Okay? As you go to higher frequencies, so that direction is higher frequencies, you can pack more information. Okay? So people are really trying to push towards the terahertz frequencies for Wi-Fi communication and so forth, so you can up your bandwidth, you can download your movies quicker and so forth. So that's one thing. But what we're interested in is the way that materials interact with terahertz radiation. So at the right there is a SD card, you know, a little SD card you put into your phone. If you just look at it, you can't see anything, right? You just see the color. If I were to shine terahertz radiation on here, and I detect the amount of terahertz radiation on the back, this is the image I get. So I can now start seeing its internal structure, the internal stuff. And the reason for that is the plastic coating here is completely transparent to terahertz. I can see completely through it. Perfect, right? So I can see all the internal electronics and copper wires and. It's used a lot in security applications where people try to smuggle organic materials, so little seahorse or plant material or whatever. Okay? It's quick, it's easy. You can use it for chemical identification, so the pharmaceutical industry uses it to identify counterfeit drugs, to identify formulation mismatches in their product line. It's used in medical diagnosis. So here's a little piece of cancerous tissue that's been biopsied, and with the naked eye you can maybe see a slight difference in the coloration. If you put it under a terahertz image, it's crystal clear. Yeah? And it has to do with how light interacts with the material. And this specific wavelength is quite useful. Okay, so we do some work in the terahertz range. I don't have an application here to show you. It's been more material science stuff. So this is what I meant with the full body scanners. Okay, so in the past, way back when, they used low energy X-rays. But we all know X-rays are bad for you. I mean, there's a reason the doctor puts a lead cloak on you that's not being exposed to the X-rays. You don't want to be exposed to X-rays. So people weren't very happy with that. And now we're on the very, very long wavelength side, a low frequency side using terahertz. And the nice thing is your clothes are completely transparent. It's polymers, right? Terahertz doesn't know about it, doesn't care. But weapons, pieces of metal, they'll reflect the light quite strongly, so it's very, very easy to detect it. Okay? If you don't do this, but if you Google terahertz images airports, you get some very revealing photos. Okay? So people aren't always that happy with it. There's been some safeguards put in place where people's privacy is being protected, because it can be quite revealing, because you literally look through somebody's clothes. Okay. Not high def, but even so. So if you travel to Europe, US, you're going through one of these, I promise you. Fortunate thing is, it's completely safe. Okay? It's really low energy photons, can't do anything to you, where in the past when we were using X-rays, not so great. Okay, that brings me then to the last thing. So I promised you galaxies to smartwatches, end off with smartwatches. Okay, so we're all pretty much familiar with smartwatches. I mean, I've got one over here, actually it's recently bought it, and you know that it's got this little green light shining at the bottom. If you, I guess everyone's different. Mine, I know, has also got the red light, but it only shines at night when I sleep. So, and the reason is you use the red light, and there's actually an infrared light as well, to measure your blood oxygen level. This one, the green, that just measures your heart rate. And I just want to talk a little bit about how it does this in both cases. Okay. Pretty straightforward in a certain sense. So the green one shines light onto your arm, and as blood pumps through your veins, the amount of blood that the light encounters changes. And it uses green light, since green is pretty strongly absorbed by the red blood. Okay? So as there's more blood, more light will be absorbed. As there's less light, less blood will be absorbed. And then you've just got a little detector over there, nothing special, that just measures how much blood do I see. And you don't need to be that accurate, because you just see a modulation, a change in the amount of light, and the change doesn't have to be very big, because it's so constant. Okay? Your heart rate doesn't vary by much over a short period of time, and you can very accurately measure your heart rate, not a problem. What I found interesting is this guy's YouTube channel, Steve Mould. What they did is they said, well, this seems pretty simple. Can I do it in another way? So they just shone a really brightish white light onto his face, and then they took a normal webcam, so your normal camera. Your normal camera has got 3 detectors in them. It's got a blue detector, a red detector, and a green detector. So they said, well, let's just look at the green detector. Let's start there. You can use any of the 3, but any of them will do. Let me just play the video. And all they did is they amplified the signal. So if they see a small increase in the green signal, they multiply it a little bit to amplify it. And if they see a small little increase in the red signal, they multiply and amplify that, right? So you can do that quite easily. So if you look a little bit sickly, if you do it like that, that would be great. But the amazing thing is, if you compare the observed signal, right, so the green here is the signal they get by integrating that green face, and the white signal is an ECG, so electrocardiogram, right, where they actually physically measure your heart rate. And that matches, not just pretty good, it matches perfectly. You can actually Google this idea. There's lots of Python scripts available that you can actually implement on your own computer's webcam to do this. Right? It's actually pretty straightforward. It might seem a little bit silly, but it's actually got some really interesting applications. So imagine you've got a premature baby, right, in a hospital. You don't want to go sticking electrodes and stuff on them. You actually want to keep the environment as sterile as possible, right? But still you want to monitor the baby's breathing. Brilliant. You shine a light on them, you put a camera on them, done. Okay? Non-contact, non-invasive, kosher, the whole thing. Okay? Pretty good. So it seems a bit silly, but it's got some real applications. And what I really like about this is how simple it is. You take a webcam, okay, which is your cell phone, and you take a light, and just do a little bit of analysis of the data, you can get some real biological information out, which I think is very cool. So this is another something that we're always interested in here at our Laser Research Institute, is using simple techniques to do quite complicated spectroscopy, if you want. Okay, so that's the green light. Okay, what else can your smartwatch do? Well, strictly speaking, a lot of them can actually also measure your respiratory rate. And I found this interesting because I was always wondering, how does it do it? Turns out, a bit of a cheat. When you breathe, your lungs expand, obviously, taking some air. As you take in some air, there's less space for your heart to beat. Okay? So it needs to be a little bit stronger, a little bit faster, to get the same blood through the rest of your body. So all they really do is they monitor your heartbeat. and they look for those small variations in your heartbeat. And those variations in your heartbeat, they can relate to your respiratory rate. Okay. And since your heartbeat, depending on how fit you are and resting or whatever, is maybe 60 beats a minute, your respiratory rate is about 15 breaths a minute, ballpark, depending again on what you're busy with. It's easy to separate out the signals and actually to get a relatively good estimate of what your respiratory rate is. Right, blood oxygen level, the last things that we've got there. Okay, so what do? They take a red LED. Why a red LED? Well, they take a red LED because if you think about your blood, it's red, right? And the more oxygenated it is, the redder it is. Okay? Simple as that. You've got very, very oxygenated blood. It's a beautifully bright red. If I have less oxygenated blood, I get a lower signal. And if I have more oxygenated blood, I have a higher signal. Simple as that, right? The redder the light is, the more light will be reflected from my red LED. Pretty straightforward. However, this is a problem because now I want to not look at a change in signal. So remember when I was looking at the green light, I was looking at a change in signal. There's either high reflections or low reflections, and the period of that change gives me my heart rate. Now I want an absolute signal. This is a different proposition. Because if I now put my watch like this, or I move it up my arm, lower my arm, that signal will change. Okay? It's not going to be constant. So how do I know what is the correct signal? And that's why they put two LEDs in there. Not just the red one, but a near-infrared one as well. And the reason can be explained from this graph. So this is the absorption spectrum of hemoglobin, right? The stuff in your blood which carries the oxygen. Red LED round about here, all good. So if I've got oxygenated hemoglobin, so the oxygen is there, my absorption is very low, which means my reflection is very high. I get a high signal. If I've got just the hemoglobin, no oxygen, my absorption is very high, so my reflection will be low, so it'll be down here. Cool. What I see though is on this side, in the near infrared, the difference between these two curves have been inverted. So here my oxygenated hemoglobin absorbs strongly, and my deoxygenated hemoglobin doesn't. Okay? And I can use this. I can use this by introducing another LED. There we go. So I've got one LED that measures the reflection of my red, and this one measures the reflection of my infrared. As my oxygen level decreases, this one will decrease and that one will increase. And I can look at the ratio of these two in order to get a measurement. And what's nice, if I misalign my sensor such that it's not giving the same signal, they will move together. If I place it somewhere else, because they're at the same position, they will move together. Their signal will go up and down in the same fashion. So I can always consider the ratio between these two signals to get a measure of the blood oxygen level. And I think that's very nifty. Okay? Sometimes called differential spectroscopy, where you take two light sources and look at the ratio between these two. And this is just on a very, very nice application. Okay? And it's on your wrist. Yeah? Simple as that. Okay. Video's not always working. So this infrared light is actually pretty cool because you can use it for more stuff. So this is just a little video from that one where they took that infrared light and an infrared camera obviously, and you just look at the light transmitted now through your arm. So you can imagine this is a completely non-invasive technique to do imaging, internal imaging. If you've got a internal bleeding in your arm or whatever the case may be, or a slight growth, or you can just stay around. It's trivial in a certain sense, right? But it's really, really powerful. I'm taking an infrared light, and because I know it's transmitted very well through skin, and absorbed by the blood very strongly, I can get this amazing contrast image in a trivial manner. So it's really, really powerful. And that's, I think, why I like spectroscopy so much. It's taking light, which we've got all these amazing sources for now, picking my parameters for my light, and then doing something interesting and worthwhile. However, one question which always pops up when you talk about smartwatches is how accurate are these measurements actually? You know? So, it's all good and well to measure the heart rate, to measure blood oxygen, and so forth, but to what degree? And if you search for this, then this is basically the hits that you get. Right? And one of the problems with this type of technology, and it's always the problem with this type of technology, it's mainly developed in the US and in Europe. The people in the US and in Europe look a lot like me. Okay? They don't look a lot like the majority of people in Africa or South Africa. This is a problem. And this is a real problem. Okay? We've got work to do. The reality is a lot of this, if you've got a darker pigmented skin, a lot of this light will be absorbed, so your signal decreases, so you've got to think carefully about how you analyze the data. And this is a reality. It's a reality we've got to deal with, but it's also an opportunity. It means we can really think about developing solutions for us, for ourselves, for our environment, okay? Not just taking stuff from Europe and from Europe and the US and Asia, okay? Thinking about homegrown solutions, and I think that's always really, really important. Okay, so that's time to wrap up, yes? So, as I said, we've got these properties of light, these parameter space, I like to call it. We can pick and choose. Okay? You can literally go to a catalog, you can say, I want a laser with that wavelength, that configuration, that polarization, that beam profiles. Okay? And you can build your experiment accordingly. You can decide what type of interaction I'm going to be looking at. What is the information I want? Based on the information I want, I must decide on my interaction, my parameter space, and I can play around with it. So I've got this amazing toolbox, okay, in my labs, which is really fun to play around with, okay, because you've got to think ahead, you've got to be innovative. Today I looked just at the wavelength, absorption, transmission, reflection, a little bit of fluorescence. Okay, but we can do cool things like scattering as well. So where's my red one? There one. I mean, you just, red light scatters a lot, so I can get a light deep into tissue. If I compare that to a green one, green doesn't do much. Okay, can't really see anything. Same laser, the same power laser, but we can think about innovative ways of exploiting simple interactions to get really, really useful information. All right, that is my story for today. Thank you all for attending. And you are more than welcome to ask some questions. Yes, we are back there. Yeah. It's actually interesting, a good question. It's not so obvious. So, first of all, it was difficult. The gallium nitride, making pure gallium nitride and doping it, because to make an LED you need to dope it so that you can form a p-n junction. If you don't know what a p-n junction is, don't worry, you'll learn about it. But effectively you need to get very pure gallium nitride, which is difficult, and then you've got to spoil it by putting the right amount of other stuff in there as well. Okay. And that was really difficult. At a certain point, people said it's impossible, cannot happen. So a lot of guys gave up. They kept on going. And through iterative process, they finally managed it. And the nice thing about the blue LED is you can then use that as your primary light source for phosphorescence. Okay, so your LEDs, most of your LEDs that you use here, has got the blue LED, and then a phosphor. It absorbs the blue light, distributes it across the whole visible spectrum, and that's why the light is white. You can't do that with red or green. So I think the applications just were so many, and it was so obvious that the applications were going to be. I mean, your Blu-ray player, the first one that came out on this, right? Okay. Yes. Go.
You shine the laser through the photo. Could you just look at the bird again?
Okay. Let's get the right one going. Yes.
It kind of looks like it's bending.
Yes.
Why is that?
It's because the bottle is curved, simple as that. So that's refraction. So the light will refract based on the refractive index of the glass and the wine inside compared to the refractive index of the air in the side. So if I come straight in, which is difficult to do, it should go pretty straight. Okay, you can't really see it there, but more or less straight. So if I come in at an angle, it bends. And that's to do with the speed of light. The speed of the light in vacuum is fixed at 3 times 10 to the power of 8 meters per second. But as soon as you go into a medium that's more dense, it slows down. And then through effectively momentum conservation, it needs to change direction. Okay? That's really what's happening there. Just a question at the back, doesn't it? Yes, yes.
So I have a first question, which may become a second one.
Okay. All good.
With the using machine learning on like the wine fermentation process, is the idea to be constantly monitoring a barrel, or to just every now and then check it?
Yeah, it would probably not be 24/7, every second. It will probably be periodic. I mean, these processes are, the fermentation process is typically over many weeks, right? So it's a relatively slow process, so it's probably not necessary to do it like 100 times a day. The data would become a little bit. But the idea was to first of all set up this model where then if I get a new data point, I can compare it to the model, and then I can make a prediction about what is happening inside. Do I need to intervene? Is everything still on track or not? So you could have fixed data points along the way.
So I suppose I'll go to the second part of it anyway. The reason I ask is how could you make sure, or would there be any side effects related to light stimulation? So like, for example, I know ear is very sensitive to light stimulation. So like, are there ways you can fiddle with the light that doesn't happen?
Yeah, so it's not a bad question. The fortunate thing here is you think about the volume. So typically the fermentation tanks are, depends if the barrel fermented or not. Barrel fermented 300 or 600 liters, and if it's tank fermented, it's thousands of liters. So you're illuminating probably microliters, okay? Very, very little in thousands of liters. So even if you were to destroy a little bit of the wine, concentration-wise, it's going to be negligible. Do you have another question?
What you mentioned tracer maps earlier on in the slides. What exactly is a tracer map?
So that was for the. Yeah. So effectively, what I meant there was that in the cloud there's carbon monoxide, but obviously that's not all that's in the cloud. So, but if you just measure the carbon monoxide, you can use that as a tracer of the whole cloud because it's moving with the rest of the cloud. So I don't need to measure everything in the cloud to know that it's moving away. I can just measure the carbon monoxide. Since it's part of the cloud, everything's moving together. That's what I meant with tracing in that context. Yes?
When you're talking about breaking the hydrogen bonds in that medical molecule, is that an example of ablation?
No, I wouldn't refer to that as ablation. It's quite similar, I'm not going to lie. Ablation is more when you take some of the solid and you come in with a high intensity laser, and you've got your energy is enough to break the bonds of the surface atoms to the ones below them. Okay? And this is typically covalent or ionic bonds, so really strong bonds. Hydrogen bonds are actually pretty weak. It's nice to stabilize molecules like that, but that's pretty weak. So they're just little breaks. Now you come in with so much, and then you actually eject the material as well. So the material will literally fly off. It's got lots of applications. That's one way to make homogeneous thin films of the material. We use that for the laser pulse deposition. You can use that, obviously creates a very hot plasma as well. That hot plasma has got interesting spectroscopy properties as well, because you can examine the light coming off there and you can get an idea about what was in this plasma. What atoms were there, what molecules were there, and so forth. So
like the sci-fi laser effect.
The sci-fi laser effect, that's ablation. When you start drilling holes and stuff, that's ablation. Yes?
Again, you spoke about dealing with. You spoke about the CO clouds, the galaxies and stuff. You spoke about how you could isolate the wavelengths that were involved with like in specific vibrational modes. How can you isolate that kind of data when like obviously all the molecules vibrating in different modes.
Yes, so I was a bit naughty here. I didn't go into that detail because there's something on time. So what they managed to do in the lab here, and it's a really important distinction, doing high-resolution spectroscopy like this is very, very difficult. If you look at the differences in the wavelengths, it's tiny. So let me try and see if I can get back there. Really, really small. Okay, so this is, okay, it's really small. So we're talking tens of picometers type of stuff. Tiny. So building a spectrometer to do that is very difficult. You can take lots of money, you can do it. What they do is they rather change the wavelength of the laser. Okay, and that's also not easy because you need to change it very, very accurately. So first of all, your laser needs to emit at a very specific wavelength, so not a large bandwidth, so very, very accurately. And then you need to move that. And there's techniques we can do it. You can do it, these gratings that you've got in front of your eye, if you take a bit higher quality one like that, then you can set it up such that the light is only reflected of a specific wavelength, only reflected in a specific direction. And you use that effectively to seed your laser, so that only that wavelength is amplified. If you change the angle, then it's a different wavelength, which is reflected back. And so that seeds your laser. And so by angle tuning your grating slightly, you can change what wavelength is amplified and what is the wavelength then on your sample. Okay? In this specific case, there's a lot more process as well to get to these very, very short wavelengths, because you don't get lasers at this wavelength, so they need additional processes to get there, which makes the experiment very technically very difficult, which is also one of the reasons why nobody done it before. It's difficult. Not easy. You do a lot of difficult stuff, so other people can do it. But yeah, that's it. Now to get it very narrow and very accurate, again, there's processes involved where you've got to measure it against an external reference so that you know what wavelength am I at. Otherwise you can't calibrate these things. So in all these stories I told you, it's not the whole picture. Okay? Simple as that. I can't tell you the whole picture. You go read the papers. Then you'll probably still not get the whole picture, but you'll get a bit more of a flavor. So I've tried to give you a bit of an idea about what is involved in all of these processes. Yes?
I just want to ask quickly, when you were mentioning about the spectrum and of the fact that we are moving towards the terahertz time to involve or get more things on that spectrum. You mentioned that the X-ray, it's kind of problematic in the sense that, well, it's a problem for the human body.
Yeah.
At what point on the spectrum does it actually become a problem? Because I'm assuming it doesn't immediately start at X-ray, or maybe it does.
Yeah, so it's six of one, half dozen of the other, I guess. It's not such an easy question to answer. If you look at the electromagnetic spectrum, when we start getting here into the violet, okay, didn't talk about it, but of course, light we can describe as a wave or as a particle, and when we just talk about a particle, we talk about photons. And as you move down in wavelength, the energy per photon starts increasing. Okay? At some point, the energy becomes enough that when it gets absorbed by the human body, it can start breaking bonds. Typically, that's here UV, let's say 300-ish nanometers. Let's say DNA absorbs at 200, and where's my biologist friends? 270 nanometers, something like that. So if it absorbs energy, it means it now forms a radical, which means it can react and then bonds can break. So if you're about 270, 290, something like that, it starts getting bad. Above that, some proteins and things like that start absorbing light. Again, if it absorbs light, it's got excess energy, it can form a new bond, it can react, things can start getting wrong. But above 400 and above, we typically don't worry about. The ozone layer takes care of everything, I think about 360 nanometers above. So we get a little bit above 350, 360 to 400, which causes you sunburn. So you put some zinc oxide on there, zinc oxide, nice reflector, blocks all the UV rays, you don't get sunburn. So a bit of spectroscopy in the suntan ocean as well. Okay. But yeah, so we have to take care. It's not a clear cut-off because it has to do with which molecules are going to interact with the radiation. And the intensity, how much of it? Yeah. So in this case, we typically talk about dose. If you're not in the sun for a long time, not a problem. If you lie like a lizard there the whole day, you get a bad sunday. So, yeah, dosage is important.
Great. I just want to say thank you to everyone for coming out, and also thank you so much, Dr. Neethling. We have something